Well, thank you all for coming. Today, I'm going to talk about my project for the summer, which is to synthesize with Agarose Microparticle mimicking for the testing purpose of Microhammer. And Professor Megan T. Valentine is my faculty advisor. Luke Patterson is my mentor. Traumatic brain injury. Imagine if you were doing a front flip and land on your face, just like this person right here. What will happen is you will probably have traumatic brain injury. It is caused by a bump, blow, or joint to the head, or a penetrate head injury. And symptoms can include impaired memory, sensation, movement, or emotional function.
I'll attest to that. All of the above.
Based on CDC data, in 2010 alone, cause of death is more than 50,000 people in the US. Our approach is to understand TBI one cell at a time by applying dynamic force to a single cell level. So we can model traumatic brain injury, and I don't have to do a front flip. We can also improve our understanding of the load of impact and pressure load on the brain cell. So, as you can see, the tool we have right here is Microhammer device. It's designed and built by Luke Patterson. The channel of Microhammer is 18 micron. So our task is to synthesize gel particle passing through the channel and get hit by the hammer, so we can characterize our Microhammer device. Why we use Agarose gel? Because it can create similar mechanical property and the size as a stem cell, and it's cheaper and easier to handle than a living cell. We can also characterize our Agarose gel first, and then we can use that data to characterize our Microhammer. So later on, hopefully we can improve the equipment design. General procedure. First, we are using a reverse weight volume concentration to control the mechanical property of the gel we synthesize. And we will heat them up. So all the gel right now is in liquid phase. Once that is done, we use micropipette to pipetting one drop at a time at the oil, which we will be applying shear force on oil. So oil applying shear force on the droplet and break down to a further part. We can also add fluorescent microscope beam just for the purpose of taking a fluorescent image. As you can see right now, we're changing the time of ball tacking and sun K to control the size. Once that is done, we will separate our gel from oil and put them on centrifuge, spin and fill around, and pipette it out of it. Because all the particles will be pushing down the bottom, so we can pipette them out of it. We also have filtering method, which haven't been successful yet. As you can see, the traditional method is to put a bunch of Agarose particles with different size and different shape, and push them through the filtering paper. So the bigger one will be on the left side, and whatever size we're trying to get will come out to the right. And it has been proved now very effective. As you can see, filtering paper before, the pot is clear, there's nothing stuck in it. And filtering paper after there are like some tiny particles stuck in it, and same as this one here, just like your sink gets stuck after a while. After we improved the filtering method, which I took the idea from some home cooking technique. As you can see, we first have large Agarose droplet on the left side. The difference here than before is we are using droplet. We are not using particles. Droplets, they are not as fragile as particles, and we will slowly push them through the filter paper. The pod help us to break down droplets into a smaller size. And once droplets are pushing to the right side, when they reach gel point, particle form. That's the basic idea. Although we still need more experiment to optimize this method. So let's take a look at particles. Well, that's just a human hair. I took it for reference. At first, we've seen a bunch of circular shaped stuff. We don't know if that's particle or it's air bubble. That's when we're using fluorescent microscope. Once under fluorescent microscope, air bubble is all dark. And that's the way we distinguish Agarose particles and air bubble. We also have a picture here that shows bright field of Agarose particle come in different shape and size. In this image, the purpose of fluorescent microscope is even clear. The more all the particles shows a brightish color and the background all dark. That help us to identify the particle and the particle size. So right here we have a picture of aggregation. This picture is taken once I pipetted the solution on the filter paper. So there are a bunch of particles stuck in it. I'm pipetting some of the solution out of it, and then take a look at it under the microscope. You can see the group of particles are aggregating with each other, and then that's what causes colliding. And then this is just a normal aggregation under the microscope without going through any filtering process. So for that issue, I did some research, and some of the people suggest by adding a nanoparticle in the solution might help prevent aggregation. I still don't know why that might help, but I give a try. Although we don't have nanoparticle, we have 0.2 micron bead. After adding, this is what the result looks like. It seems like yes, they are not all aggregated together. It might work, but more experiments still needed for confirm the result. And that particle right there is approximately a 15 micron particle. I believe that one will be useful for the purpose of testing microhammer. We also tried a different technique by coating particles with 0.2 micron beads. Although it has no purpose for looks experiment, but it might be useful later on, who knows. And this is one of the picture I took for the traditional filtering method, or the one come up first, and that is our improved method. You can see improved method somehow control the size of particle. Hopefully we can get more uniform sizes, and the range of difference will be much smaller later on. In conclusion, we synthesize 1 to 10% weight volume percentage concentration Agarose particles in appropriate size range. Our future plan is to characterize mechanical property of the particle and to explore more on the alternative method, maybe to do some improvement later on. Acknowledgement. I really want to thank Luke for everything. Without him, I will have no idea what's going on. with him, I have some idea what's going on. And all the crews in Professor Megan Valentine's lab, especially Bugla, is the person who teach me the general procedure, how to synthesize particle. And Emerald, Lana, every single person in Professor Megan's lab are very helpful. They all give me a different kind of advice. And especially Professor Megan. We saw her at one here. Also Turner's lab. They're just bunch of wonderful people. I don't really get a chance to meet yet. They are probably not here all the time. They're busy doing their stuff. We know work on the same project. I also want to thank Wendy for all the help with the presentation and everything, and the Jens for poster advice, for poster suggestion, everything. So thank you for coming. Have a wonderful day.